Hi everybody. On today's show, we look at fractions that have polynomials in the numerator and denominator. It's not as scary as it sounds. So this is lesson 1 of Unit 2. And Unit 2, there's kind of 3 parts to it. The first part, we look at these rational expressions, then we look at radicals, and then we look at 3 by 3 linear systems. So there's 3 little segments here in Unit 2 that form up this unit. So hopefully you got your purple packet already, and let's get into lesson 1. So write two fractions that are equivalent to 1/3. So yes, we're going back to 7th grade here for a second. Equivalent is a big idea in this unit. It looks different. It looks different, but has the same value. That's what it means to be equivalent. Things look different, but has the same value. So if I want something that's equivalent to 1/3, we can all agree that 2/6 is equivalent to 1/3. If I multiply by, I don't know, 5, we get 5/15. That's the same as 1/3, and so on. There's infinitely many things that you could, there's infinitely many rational numbers here that are equivalent to 1/3. How do we use an area model to justify this? So here's a rectangle, and I'm going to split into thirds. There's 1/3. Well, if I take my model here and cut it like that, we see I now have 2 out of 6. So 2/6 is the same as 1/3, because all I did there was I added in that extra line. This is just a quick review of fractions from your middle school days. So, which of the following numbers are rational numbers? When you hear the word rational for the rest of this course, and you should know this already from Algebra 1, but that was such a long time ago. When you hear the word rational, we need to think of fractions. Rational is ratio. It's the ratio of two integers. The ratio of two integers. So which of these numbers are fractions that are the ratio of two integers, two nice numbers? 3/4 totally is a rational number because it's 3 to 4. 3.14, it's a decimal that terminates. This is 314 over 100. I can write it as a fraction. That's totally a rational number, so yes, that works. Pi is irrational. Pi is an irrational number because its decimal expansion never ends and never repeats, so I cannot write pi as the ratio of two integers. 5 over 0, this is bad. Warning, warning, warning. We're dividing by 0. We can't divide by 0. We cannot divide by 0, so 5 over 0 is not a rational number. The square root of 17 is no good either, because 17 is not a perfect square. Seventeen is not a perfect square, so we will not consider that a rational number. Again, the same thing here. The 1/2 is fine, but the plus 5, radical 5 over 2 is not good. So that's not a rational number because the square root of 5, again, is not a perfect square. -1 works because that's -1 over 1. And 0 works because that's 0 over 1. So what are the rational numbers? It's numbers in the form a over b, where a and b are integers. Rational numbers are going to pop up again this year in January when we talk about exponential functions. So it's a good idea that we get this idea that rational is talking about things that are in fractions, where I have an integer on the numerator and an integer in the denominator, and b is our denominator cannot be 0. We have to exclude our denominator from being 0. So, what's a rational expression? Rational numbers we know and love from middle school. Rational expressions are in the form, so it's an expression in the form p over q, where p and q are polynomials. So it's a fraction, but there's a polynomial on the top and bottom, where p and q are polynomials. And q cannot be 0. So what's a rational expression? It's an expression in the form p divided by q, p over q, where p and q are polynomials, so I have a polynomial up top, polynomial on the bottom, and we have to make sure that q is not equal to 0, because we can't divide by 0. What are some characteristics? Rational expressions work just like rational numbers. So you can add rational expressions just like we added fractions in middle school. So they have the same structure. You can multiply rational expressions just like you multiply fractions. You can divide rational expressions just like you divide fractions. So rational expressions is extending our idea of rational numbers to having polynomials on the top and bottom. What are some examples? Well, believe it or not, 3/4 is also a rational expression because 3 and 4 are both polynomials. X squared minus 1 over x plus 1. That's a rational expression. A squared plus 2b over, I don't know, 5xy plus 7. Anything as long as the bottom is not 0. So if I had x squared plus 1 over 0, that's a non-example because you can't divide by 0. If I had the square root of x over x plus 1, that's not, square root of x is not a polynomial. So the square root of x is not a polynomial, so it's not a rational expression. So rational expressions consist of lots of things, x plus 3 over 2. As long as you have a polynomial in the top and a polynomial in the bottom, and as long as you're not dividing by 0, you're good to go. That's what rational expressions are. We have a polynomial up top and a polynomial in the bottom. So for what values of x is the rational expression? Clearly there's a polynomial up top and a polynomial on the bottom. Undefined. Undefined is when do we divide by 0? When do we divide by 0? So if I look at this expression here, well, I see x squared minus 36, and I instantly say, wait a minute, that's the difference of perfect squares. Over, well, the bottom's a trinomial, so I'm stopping and asking myself, what multiplies to negative 12 that adds to negative 4? What two numbers multiply to negative 12? Well, that's going to be x minus 6 and x plus 2. So right now, we can tell when this is undefined. When is the denominator equal to 0? What makes my denominator 0? Well, that would be x equals 6 and x equals negative 2. These values are what make the expression undefined. If I try to plug in a 6 up here, I'm going to get something over 0. If I plug in a negative 2 here, I'm going to get something over 0. So these are the values that make the expression undefined. These are bad values that we have to throw out. You cannot plug in a 6. You cannot plug in a negative 2. If you try to plug those in, you make your denominator 0. So undefined means you make your denominator 0. Those are the bad values you need to get rid of. Then simplify the expression to lowest terms. So notice that we have a common factor of x minus 6 and x minus 6 on the top and bottom. So I know right now you want to say those two factors cancel out, but no, we don't say that. Things either add to 0 or divide to 1. In this case, x minus 6 and x minus 6 divide to 1. So this expression is really equivalent to x plus 6 over x plus 2. That's what the expression is equivalent to in lowest terms. So whenever we work with rational expressions like this, we really want to factor them. Factoring these rational expressions lets us see common factors that we can simplify, as well as know when the rational expression is undefined. When is the denominator equal to 0? When is the denominator equal to 0 is our big idea here. So reduce the following rational expressions to lowest terms, and then identify the values of the variable that make the expression undefined. Let's try the first two together, and then I'll let you try the next two on your own. Or maybe we'll do A and C together, and I'll let you try B and D. We'll see. So whenever we deal with these irrational expressions, the first thing we want to do is see if we can factor them. So if I look up top here, I'm asking myself, what multiplies to -6 that adds to -1? That's x minus 3 and x plus 2 over, I've got a GCF here of 5x that I'm taking out, and I'm left with x plus 2. So first, let's deal with undefined, the values that make the expression undefined. What values make this expression undefined? Well, when is my denominator equal to 0? When does 5x equal 0? I cannot plug in x equals 0. X plus 2 equals 0. That's x equals -2. If I try to go and plug those numbers in, I'm going to end up dividing by 0. These undefined values make me divide by 0, so those are the numbers I have to get rid of. And we see these very easily simplify. Those x plus 2's divide to 1, so this expression is really equivalent to x minus 3 divided by 5x. Let me look at C for a second here. I actually want to talk about C, and then I'll let you try the next two on your own. So let's jump to C. And I want to factor the denominator there as the difference of perfect squares, so I get x plus 3, x minus 3. Our undefined values are pretty straightforward. Undefined at x equals -3 and +3, so plus or minus 3. You cannot plug those in, otherwise you end up dividing by 0. Now here's the thing, can I divide anything out right now? Well, do I have any common factors like I did in that previous example? I had x plus 2 over x plus 2. Here, I have a 3 minus x and an x minus 3. So if I look at that 3 minus x for a minute, if I factor out a -1, I get -3 plus x. And if I apply the commutative property there, I get x minus 3. So these two factors do divide out, but they just don't divide to 1. They end up leaving behind a -1. So we have to be careful of these pesky -1s. Look what I did here. I said that I had 3 minus x. I factored out a -1, and I was left with -3 plus x. Well, using the commutative property of addition, that lets me switch the order to x minus 3. Now I have that common factor. So whenever I divide a 3 minus x and an x minus 3, they do divide out, but they leave behind a -1. This is one of the main reasons why I don't let you say things cancel out, because they don't cancel out, they divide in this case to -1. So take a minute, try working on B, try working on D, and once you guys worked on those for a couple minutes or struggled and said, help us, coach, so let's pause the video now, and I'm going to talk through the answers of those two pretty quickly. Welcome back. So in B, let's see what we can do here. I want to factor as much as we can. The denominator looks easier to factor, so I'm going to start with that. I took out a GCF there. Because the top is a trinomial, so I have to use that darn AC method. What multiplies to -6? That adds to -5. Well, that's going to be -6 and +1. So I get -3x squared minus 6x plus 1x plus 2. I can take out a minus 3x from those two, and I'm left with x plus 2. If I need an x plus 2, I'm going to factor out a 1. So my factors are x plus 2 and -3x plus 1. So when is this undefined? It's undefined at x equals -2. And what about this x squared? That's x equals 0. If you plug a 0 in, what's 0 squared? 0. So that's when this expression's undefined, and we notice that we have a common factor here of x plus 2, so this expression is really equivalent to -3x plus 1 over x squared. D. Well, I noticed from the numerator I can take out a 3. And the denominator is a little weird because we have both x's and y's going on, and we haven't really factored trinomials that have both these variables in it. But notice that it's y squared minus 2xy plus x squared. Well, if we just think about it, I know y times y gives me y squared, and I'm assuming I need an x plus x to give me x squared. And if I make both of those negatives, when you make a table to distribute these out here, you're going to get negative xy and negative xy, which gives me the negative 2xy. So factoring that trinomial on the bottom was a little bit tricky. You could have you could have treated x as a number and said what multiplies to x squared that adds to negative 2x. But I think just recognizing that structure of, well, I got y in the front seat, x in the back seat, they both need to be negative, is a pretty quick way of factoring that trinomial. But when is this undefined? It's undefined when y minus x equals 0, when my denominator equals 0. Well, y cannot equal x. Well, if I get y equals x, that's when it's undefined. When y equals x, that's when it's undefined. I can't have y and x being the same number, otherwise we end up dividing by 0. And that's what undefined means, we're dividing by 0. So do I have any common factors here? Well, we do. Those guys do divide out, but it leaves behind a negative 1. Because if I have y minus x, I can rewrite that as negative 1, negative x, negative y plus x, and using the commutative property lets me switch the order, which divides out there. So what's this expression equivalent to? 3 over negative 1 times y minus x. Or you could write that as negative 3 over y minus x. Take that negative 1 and bring it up top. So that's equivalent to this original expression. When I say equivalent, I mean they look different, but they have the same value. In all four cases here, these expressions look different than what I started with, but still always output the same value as long as the expressions are undefined. Number 4, switching gears here. For each set of rational expressions, state a common denominator. When we work with rational expressions in the next couple of lessons, we're going to need common denominators. Just like how you needed common denominators when you worked with rational numbers in 7th grade. When you added fractions and subtracted fractions, you needed common denominators. So when we work with rational expressions, it's going to be in our best interest to have a common denominator. And so get a common denominator and create equivalent rational expressions so that all expressions have the same denominator. So if we go back to our opening exercise here for a minute, we were creating equivalent expressions. We came up with this rule that a over b is the same thing. Well, if I multiply the top and bottom by 2, I got that new equivalent rational number. If I multiply the top and bottom by 5, I got this new one. So if I multiply the top by something, I also have to multiply the bottom by that same thing, because all we're really doing there is multiplying by a factor of 1, and multiplying by 1 doesn't change the value of an expression. So that's what we're going to do here in question 4, is we're going to create equivalent expressions by multiplying by 1, even though it's not going to look like 1. So let's look at the first one. I've got 5 over x minus 2 and 3x over 4x minus 8. Well, I might say, wait a minute there. That 4x minus 8 is really 4 times x minus 2. So, what's my common denominator? My common denominator is 4 times x minus 2. Everyone needs a 4, and they need an x minus 2. So this guy is set. It's got the 4 and the x minus 2. Whereas this first expression, I need a 4 on the bottom, so I also have to put a 4 up top. So what's that new expression there? 20 over 4 times x minus 2. It looks different, but it has the same value as what we started with. So just like when we were finding undefined values, and by the way, both expressions are undefined at x equals 2. Let's say x cannot equal 2 here, just to practice that skill still. We get a common denominator by saying, hey, everyone has to have the same factors in their bottom, in the denominator. B, 3 over x plus 2 and 4 over x minus 5. Now, people find it really tempting to somehow make the 5 a 2, maybe by adding 7. No, 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 no. The way that we're going to do this is we're going to say everybody needs an x plus 2, and everyone also needs an x minus 5. That's my common denominator. So this first expression, it has the x plus 2 already. I want to stick in an x minus 5 and make sure both of those are in parentheses. So if I stick an x minus 5 in the denominator, I also need one of those x minus 5s up top because those divide to 1 now, and I didn't really change the expression. The second one already has the x minus 5, so I'm going to stick in that factor of x plus 2. We're getting a common denominator here because that's how we're going to work with rational expressions in these future lessons. So we've got the common denominator here. Everyone's got an x plus 2, and everyone now has an x minus 5. If we distribute, we get 3x minus 15 over x plus 2 times x minus 5, and 4x plus 8 over x minus 5 and x plus 2. So we get a common denominator by making sure both expressions have the same factors in the denominator. C, 4r over r plus 3 and 5 over r. Now, everyone loves to just think they can add 3 to that second expression there. No, this r is really like an r plus 0. So everyone needs an r plus 3, and they also need that r plus 0, which is a plain old r. So my common denominator here is r and r plus 3. Everyone needs both of those. So this first expression has the r plus 3, so I need to multiply an r in. I need to stick an r on the top and bottom. So I get 4r squared over r times r plus 3. And the second expression here has the r factor. It needs an r plus 3 factor. So let's stick an r plus 3 factor up top. And we get 5r plus 15 over r times r plus 3. So don't think you can just magically make that r into an r plus 3. You can't unless you add 3, which doesn't really work with rational expressions, because if you add 3 to the bottom and add 3 to the top, you don't get the same number. I will show you right now. If I have 1/2 and I add 3 to the top and bottom, that gives me 4/5. I think we all agree that 0.5 and 0.8 are different numbers. They're not equivalent. So we can't add. You have to make sure everyone has the same factor. So let's pause the video here and have you work on part D as a quick little OYO. Let's have you work on part D as a little on your own or with 2 friends if you so choose so. But try to make sure that everybody has the same denominator. Welcome back. So hopefully you realize that, wait a minute, this second expression here, if I factor that denominator, it's x squared minus x minus 12. You asked yourself, what multiplies to negative 12 that adds to negative 1? X minus 4 and x plus 3. So what does everyone need? Everyone needs an x plus 3 and an x minus 4, and this guy's already got both of them. So that first expression has the x plus 3, but is missing the x minus 4, so let's stick that on the top and bottom. So we get 2x minus 8 over x plus 3 over x minus 4. This second expression here, let me switch colors, has the x minus 4. I need the factor of x plus 3. Yeah, I know it's not in the same order, but the commutative property takes care of that for us. 3x plus 9 over, I'll switch them for you so you stop panicking. That, and this last expression already has both factors, so it's good to go. 2x minus 2 over x plus 3 times x minus 4. So getting common denominators is going to be a big idea in the future lessons, so hopefully you found these 4 problems relatively straightforward. The big idea is just making sure everybody has each other's factors on the bottom. This had an r plus 3, we also needed an r, so everyone needs a factor of r and r plus 3. This has an x plus 3 and x minus 4. He had both, so we made sure that everyone had both x plus 3 and x minus 4. If we were to quickly go through and say what are our undefined values, well, that would be negative 3. So we say x can't be negative 3. X can't be 4, because if you plug those in, you would get 2 divided by 0 or 3 divided by 0, respectively, for negative 3 and 4. So we have to make sure that we always look out for those undefined values. What's making my expression undefined? Over here in letter C, that would be r equals negative 3. So we say r is not negative 3. Negative 3 plus 3 is 0. And r cannot be 0, because if we plug in a 0 to 5 over 0, we get an undefined expression. I don't think we did that for 2. What makes 2 undefined? That would be negative 2 and positive 5. We get rid of negative 2 and 5. We don't want x to equal those, otherwise we're working with undefined expressions, which are meaningless. So, your homework, work on that for the rest of the period. If there's time left, who knows how long this video is at this point, but I'm sorry I couldn't be with you for the start of Unit 2. I'll see you tomorrow. Video homework is online on my website and on Google Classroom, so make sure you check that out before tomorrow because the same homework policy is in effect for the rest of the year. Do your homework and check it before you walk into my classroom. See you all tomorrow.